Okay, hello guys. Welcome to the finally we end the section for double integral. Welcome to the triple integrals. Basically, the triple integral is the same thing as double integral. I would say the difficulty of the triple integral is actually the same as double integral, which is finding a domain and describing it precisely. And since in this case we're describing a domain in the 3D space, so it'll be even harder. And I will try to demonstrate more example for you guys to know how to translate a solid which can be described using, say, a lot of surface bounded the solid into a actual formula in mathematics in math, so you can apply it to the integration. Okay, so I won't give many definitions here. Actually, I won't give any definition here because it basically follows the same idea as the double integral. You create a Riemann sum. Sorry, you first create a grid within a three-dimensional solid, and you push the mesh to be so small so that you can evaluate the function on those small finer grid, and summing that up, you get a Riemann sum. If that guy converges, then you get the Riemann integral. And again, you have the Fubini theorem, so you can evaluate the triple integral in terms of three iterative integration. So let us start for a simple case where you are evaluating the integral on a constant boundary region, which is a rectangular domain. Okay. So we're now integrating this guy. So instead of the dA, we use dB in a two-dimensional setting. So we're integrating a triple integral of this x squared plus z squared over some 3D region. This 3D region is given by 0, 1, 0, 2, and 1, 3. So x belongs to 0 and 1, y belongs to 0 and 2, and z belongs to 1 and 3. And so by Fubini's theorem, we have that we can evaluate this guy using iterative integration. So in this case, I choose x first and then y and then z, and it won't really matter because these are constant boundaries. So changing them will not actually change the boundary. And then the simple integration algebra. For x, you get half of x squared plus z squared x, right? So evaluating x at 1 and 0, you can evaluate it again using, you can integrate it again with respect to y, which you get y squared divided by 4 plus z squared y. Plugging in 2 and 0, you can evaluate it, integrate it again by z, which you get z, because this guy is 1, right? Z plus 2z cubed divided by 3. Plugging in the upper and lower boundary, you simply get 58 over 3. And that'll be the final answer for this three-dimensional integration. So you can see that actually everything follows the same as the actually two-dimensional integration and one-dimensional integration. The hard part is when the domain is not a rectangular region. It is a general bounded region, a type 1, type 2, type 3 region. So let us go to see how we can apply this and how it practically works. So in this example, it is actually an exercise in your textbook. We want to find, so we first define E to be the solid in the first octant. So that is the octant when X and Y and Z are all positive. And the solid is bounded by these surfaces. Y squared plus Z squared is 9. That's a cylinder in the X direction. X equals 0, which is the YZ plane. Y equals to 3X, that is also a plane. Z equal to 0, that is the XY plane. So I want to see that some solid bounded by these four surfaces. And we're given that the density of this solid is given by rho xyz being z. That means that it is denser when the height increases, right? And we have to compute the mass of E. So we haven't talked about the density mass volume relationship in section 15.4, but let me briefly introduce it here. We have learned in, I assume, high school that mass is always equal to density times volume, right? Whenever density is a constant. So basically, when that particular solid is uniformly dense, everywhere has the same density. But there obviously is something where you have different density among different points. In that case, we define the mass, actually we evaluate the mass by integrating the density over the volume. Okay, so that'll be a triple integral where a density function can be integrated over the volume, and you can describe the volume using that solid. Okay, so here's the sort of the most important topic of this particular section is the strategy of doing triple integral. And I described it as outside in. So first of all, you want to describe the constant boundary. The utmost integration is always of constant boundary, right? Because after integrating, you should get a constant instead of a variable, right? So first of all, you should fix the outside boundary. It can be dx, dy, or dz, depending on your choice, but you have to find out the minimum of, say, x and maximum of x to get the outside boundary. And now it is remaining the two-dimensional integration, right? So now for this 2D integration, this is the way you do it. You fix, okay, say, let me fix our first constant boundary to be x. Then for a second integration, you have to fix y and z variables, right? So now fix a x, this x is arbitrary, say x is between 1 and 3, then fix that particular x and draw the diagram for y and z domain in terms of x. The boundary may be in terms of x, but that's okay because obviously the two boundaries inside the x integration must be of something regarding x, right? Okay, so maybe I can demonstrate this as an example to be more precise. So in this case, we have y squared plus z squared to be 9, x to be 0, y to be 3x, and z to be 0. So saying in this case, I want to fix z first. Then obviously, based on this four condition, the minimum of z is 0, right? And the maximum of z is determined by this guy, which is 3. So usually it should be minus 3 and 3, but we're choosing configuration from the first option, so z has to be positive. So that is maximum being 3 and minimum being 0. So now that's what we have performed the first step. The second step is to fix a particular z and figure out the domain for x and y. So in this case, let us fix z. Then what I want you guys to do is to draw out every boundary surfaces in terms of a line. Because now we already have a section, right? We cut the solid at level z. And so you have a two-dimensional diagram. I want to plot all that two-dimensional diagram. So first of all, what is y squared plus z squared equals to 9 on this diagram? It is a straight line, right? Because these are constant. So y is actually equals to plus square root of 9 minus z squared. And this blue line will be x being 0. And this guy will be a straight line, y equals 3x, where x equals 0. Oh, 0, 0 does not contain, it's not contained in this diagram because it only regards z. So what is the domain bounded by these surfaces? It is basically this triangular region, right? So at level z, you're computing the integral over this rectangular region. So say we denote this by omega. The omega is basically, I regard this as a type 1 domain, then it'll be something like this. We fix the x boundary, which should be 0 towards 1/3 of square root of 9 minus z squared. Note that z now is a constant, okay? Z is fixed. And x in this case will be all the way from 3x to this particular constant. And if we regard it by a type 2 domain, then y will be going from 0 all the way to 9 minus z squared, taking square roots, and x will be all the way from 0 to y over 3. So both of these works. So this is what I'm trying to say. First, you find the boundary for one variable, in this case z, that is a constant boundary, and then you fix z, an abstract number between the boundary that you find in step 1, and then you figure out each curve determined by the surfaces given z being a constant at each z, and then you can describe each domain in terms of z. So perhaps I should make this more precise. Let me denote this by omega z. It corresponds to a particular value of z. Okay, omega z. Right. So now we can combine this definition together with the previous boundary of z to gain a nice inequality description of the solid. So xyz belongs to the three-dimensional space where z goes from 0 to 3, and you'll simply copy everything from here. Okay. You can obviously also do this. In this case, I choose type 2. And yeah, basically two thing works the same here because the integrand now is really simple. So let us do the integral. We know that the mass will be the integration of the density over the volume. So let us use Fubini theorem to evaluate this triple integral. The first thing obviously will be dz. that is a constant boundary. And for interior two-dimensional integration, you can choose either this type 1 description or type 2 description. I, in this case, choose the type 2 description. So y has a fixed boundary in terms of z, and you have a boundary with respect to y in the x integration. And then it's algebra. So this guy does not depend on x. You simply have yz divided by 3 integrating over y. And then you have the indefinite integral y squared z divided by 6, plugging in these values, which gives you z times 9 minus z squared. So that's a polynomial, right? Doing the final integration, you will give yourself 27 over 8 gram, because the unit of the density is gram over unit cube. So let me emphasize this again. There's only 2 steps to do. One step is to first evaluate the boundary for a particular variable. It can be x or y and z, depending on your choice. And then for the rest of the 2 variables, you drew out every surfaces that is describing that solid. Those surfaces will now be a curve, so it'll be very easy to draw. And don't forget that the variable that you find in the first step will be a constant. So in this case, this will not be a cylinder, but a straight line, y equals to plus or minus square root of 9 minus z squared. Okay. Right. So now let's do the second example. We want to find the volume of the solid enclosed by these 2 paraboloids, y equals to x squared plus z squared, and y equals to 8 minus x squared minus z squared. So if you have like a nice imagination of these 2 surfaces, it basically is this paraboloid, y equals to x squared plus z squared, together with one going downwards. So it looks like almost like a ball, and they intersect at the level of 4. But if you don't have that imagination, it's okay. We can do it as what I previously described, to evaluate everything in a 2-dimensional version, so you can have a good visualization on that. So obviously from these 2 guys, we know that y can at most be 8 and at least be 0, right? So that is the natural boundary for y. And we choose y due to the fact that you have a symmetry between x and z. So I want to choose y first. So first of all, we see that when y is less than 4, then this guy will be less than this guy, right? So the blue curve will be the x squared plus z squared equal to y, and the red curve will be the x squared plus z squared equal to 8 minus y for this fixed y. Okay, so that is the case where you have this guy, and the upper ball actually have a larger radius when y is less than 4. And for the upper version, when y is between 4 and 8, we see that the lower ball actually has a larger radius in the upper ball. So we know that we want to find everything close by these 2 paraboloids, right? So we want to choose the interior one. So whenever y is within 0 and 4, we want to choose something like x squared plus z squared less or equal to y. And when y is within 4 and 8, we want to choose something like x squared plus z squared less or equal to 8 minus y. So the solid can basically be described in this way. This is a union of 2 parts, which is the lower part and the upper part. The first part can be given by whenever y is between 0 and 4, and you're finding x and z within these 2 values, 0 and 1. The second part is when, sorry, I didn't write this correctly. There should be an extra condition. So as I mentioned, the second part is when the height is larger than 4, and that the condition for x and z are x squared plus z squared less or equal to 8 minus y. Okay, so the upper part and the lower part. And now we can do the integration. So the volume of that particular intersection of those 2 paraboloids can be evaluated using 1 over that domain. Okay, 1 will be the corresponding integrand, and you can get the volume using that integral. So for Frobenius theorem, you can choose arbitrary order of integration. In this case, we have chosen y to be our exterior integration, right? The outmost integration. So you have 0 to 4 and 4 to y. And the double integral within those 2 regions are different. One is from 0 to y, which is this case, And 1 is when x squared plus y squared goes from 0 to a minus 1. Okay? And now you can do something variable, maybe polar coordinate, but actually this is not necessary because this is basically a disk, right? A disk of radius y. Sorry, of radius root y. So the area for that disk will be pi r squared, which is pi times root y squared, and that's pi y. The same thing happens for latter term, that is pi times 8 minus y, right? So at the end of the day, you can get that the volume will be 16 pi unit cube. So this is a way when you observe that you have a really nice integration, which you don't really have to evaluate it using algebraic technique, but geometric intuition. Okay, so that is perform another example to try to see how you can translate this integral back and forward, how you can describe a region with various different conditions. So in this case, this is also an exercise from the textbook, a very nice one. So evaluate this integral. F is an abstract function. We evaluate x from 0 to z, z from y to 1, and y from 0 to 1. So basically, domain can be interpreted as 0 less or equal to y, less or equal to 1, y less or equal to z, less or equal to 1, x larger or equal to 0, and less or equal to z. So the problem is to write 5 other iterated integral, which is equivalent to this I. So first of all, note that why are there 5 iterated integral that is equivalent to this integration? That's because you have dx, dy dz, or dz dy. That's two different choice of integration order, right? And for each dy dz, you have different two options. So that gives you 6 options. 3 times 2 times 1. That's 6 options, right? So basically, we're trying to write this integration into, say, dx dy dz, or dz dx dy, and so on and so forth. So first of all, perhaps let us choose the easy, simpler version that can be translated from this guy. So again, how do you write down this integral? You fix the constant boundary in the utmost integration, and then you draw the picture in the interior two-dimensional integral. So in this case, let us fix y first. And now I want to switch order between x and z. So first of all, I should draw out the domain of x and z. Let us draw the curve that I described before. So where is z equals to y? Y is a constant now, right? So z equal to y is a constant here, a horizontal line. And z equals to 1 is somewhere here. X equals 0 is somewhere here. X equal to z is a slanted line. So this trapezoidal area is what we're integrating for a fixed y. Don't forget this. So now this is a description in the xz term of a type 2 region, right? We describe z for a constant boundary first, and then x is a functional boundary. And now reversely, we can describe x for a constant boundary and z for a functional boundary. However, this is not entirely a type 1 type of domain because you have to bisect those domains because these two guys have different z boundaries. Whenever x is within 0 and y, then z will be within y and 1, right? That is this case. And when x is within y and 1, then z is lower bounded by x and upper bounded by 1 again. So E will be the union within these two domains, these two type 1 domains, to be precise. So we can now rewrite this I to be, you have the same boundary for y, and for the first version here, x goes from 0 to y, and z goes from y to 1. For the second integral, x goes from y to 1, and z goes from x to 1. Okay? So these are the two cases where you fix the constant boundary to be y, and you swap the x and z coordinates. One is regarding x as the functional boundary, one is regarding z as the functional boundary. Okay, so now let's do this again. Let us fix z to be the constant boundary. Then we're dealing with x and y, right? So let us again draw out all of this guy, right? So now z is a constant. When y is 1 and y is 0, you have these two guys, y is 1 and y is 0. Oh, sorry, y is 0 and y is 1. And for this guy, z is a constant, right? You have y equal to z. That is the only thing regarding the x and y domain. And for x, it is within 0 and z. So x equals to 0 and x equals to z. So we actually have a square where the side length of the square is actually z. So x and z, x and y are between 0 and z. And since this two guy actually has constant boundary, it is both a type 1 type 2 region, right? So we can simply write down the two corresponding integration as the following. You have z as a constant boundary between 0 and 1, and y and x are off boundary 0 to z. And you can solve that directly because those are symmetric, right? You have the same constant boundary. Okay, so now we have achieved 4 different types of integration. One is this, one is this, one is this, and one is, oh, sorry, my bad. One is this, one is this, one is this, and one is this. Those are 4. So lastly, now let us fix x to be the exterior boundary, exterior integration, the outmost integration, where x obviously goes from 0 to 1. Then we have to draw out the domain for y and z. So basically, by the previous observation, in the second case, you can see that x and y share some symmetry, right? So actually, you can see that the diagram here is very much similar to when we set y to be of constant boundary. So again, let us draw out every curve we have. First of all, for the red thing, we have y to be 0 and y to be 1. So y to be 0 and y to be 1. And now for z, we have z to be y and z to be 1. So z to be 1 and z to be 1. And lastly, we have z to be x. So z to be x here, the yellow curve. Don't forget that now x is a constant. So this is a horizontal line, not a slanted line. So again, we're dealing with the trapezoidal region. If we regard this as a type 1 domain, where we fix y to be of constant boundary, 0 to, constant boundary, so 0 to 1, then we have to split this z into 2 sections because these two guys have different function boundary. For when y is between 0 and x, you have z between x and 1. For y between x and 1, you have z between y and 1. So those are the 2 trapezoidal domain. And for the third cases, when you regard this guy as a type 2 domain, so we fix the boundary for z first. Z goes from x to 1. And then for every fixed z, you have y going all the way from 0 towards z. So that's 0, that's equal to y, that's equal to z. So we have the final 2 formulas for the iterated integral. One is 0, 1, correspond to x. And y goes from 0 to x, y goes from x to 1, z goes from x to 1, z goes from y to 1. Okay, those are the 2 different integral on this rectangular area and this triangular area. And by describing this as a type 2 domain, you have y goes from, wait, okay. Yeah, so y goes from 0 to z, yeah. And z goes from x to 1, and x goes from 0 to 1. Sorry, it's a little bit complicated, so I get confused for a second. So yeah, there will be your 6 different types of integration. And this is a very, very good exercise for you guys to know how to describe the domain in different ways. So as I mentioned, the strategy will be fix constant boundary first, and then you have a nice visualization of this in a two-dimensional version by setting, in this case, say z to be constants. Okay, in this case, y to be constant. Sorry. Okay, so lastly, let us do a very interesting example. We want to find the volume of a ball of radius r. So recall that in the previous video, we have found the surface area for a sphere, right? Now let's do the volume. So we have actually a lot of technique to do this for now. In the previous section, I think again section 8 or chapter 8 or something, we have a so-called washer formula. When you're rotating a curve around the axis, you can compute the corresponding volume obtained by that surface, obtained by that solid. So in that case, it is actually really nice. The formula is simply pi f of x squared dx. And that is also very simple to derive because pi r squared is simply the area of the disk, the rotating disk. And the thickness of that disk is given by dx. So multiplying the area of the disk together with thickness, you get the volume of that small disk. Adding up those disks, you get the volume, right? So in this case, it's very simple because f is given by square root of r squared minus x squared, and then you get nothing in the square root, and the integration is really simple, which you get 4/3 pi r cubed. Now we have the double integral technique. We can actually consider this guy bounded, we can actually consider the ball bounded above by z equals to r squared minus x squared minus y squared taking square root, and in lower bound is square root of r squared minus x squared minus y squared taking negative value. So we basically integrate the upper domain and lower domain, and we subtract those two guys, where we integrate on the region of the xy plane, which is x squared plus y squared less than r squared. Okay, r squared, sorry. So that will give you the volume for the ball, right? And yeah, then it is basically simple integration. The only technique we use here is that we translate this into polar coordinate because it seems like a symmetrical, a radially symmetric region. So we have extra r, don't forget that. And then it is simply u sub, which you can get the antiderivative to be minus 2/3, r squared minus r squared, 3/2. By plugging in the corresponding boundary, you can get the same formula, 4/3 pi r cubed. And now we have the triple integral version. So we can actually describe that using a very simple kind of domain algebra. The x and y are obviously within 0 and r squared, right? X squared plus y squared is within 0 and r squared. And again, z can be described by the upper boundary, square root of r squared, r squared minus x squared minus y squared, and lower boundary, the minus sign of the upper boundary. So we see that the volume is integrating over that particular solid over the integrand 1. And in particular, by Fubini theorem, you can split this integral into iterative integration, right? And the z coordinate obviously corresponds to this upper and lower boundary, and the xy domain corresponds to this disk boundary. And we see that this guy taking dz integration is actually this guy, right? So then it actually behaves the same as the double integration, and you get obviously the same answer. So this triple integral technique here is not really useful in the sense that it actually can be characterized already by double integration because we can subtract the upper bound and lower bound, right? Okay, so let me give some formula here to sort of associate what we have done already. Let Brn to be the ball in Rn with radius r. So for example, when n is 1, what is the ball on the straight line? So don't forget the ball is basically a collection of points on some set, which is of distance less than r within the origin. So our real line is simply this domain, okay? A straight line with length 2r. So we can see that the volume of that would be 2r. And we add SR n minus 1 to be the sphere inside Rn of radius r. So for example, what is SR0? That is a sphere on the real line, right? But the sphere on the real line is the boundary of the ball, which is this point and this point. So that is 2, okay? Because there's 2 points. It's a counting measure. We count the points, 1 and 2. And what is the sphere in R2? It's a circle, right? And the sphere in R3 is the sphere that we imagine. And the ball in R2 is the disk. The ball in R3 is the ball we imagine, right? And so for now, we have these formulas. The volume for the one-dimensional ball is 2r. The volume for a two-dimensional ball is pi r squared. That's the area of the disk. The volume for the three-dimensional ball, which we have just derived, is 4/3 pi r cubed. And we have just mentioned that the volume for the zero-dimensional sphere on the one-dimensional real line is 2, because there's 2 points. And the volume for the one-dimensional sphere, which is basically a circle, is 2 pi r, right? That's the circumference of the circle. And lastly, the volume for the two-dimensional sphere, which is the boundary for a ball, is 4 pi r squared. So you can note that we actually have a nice relationship between these two guys. The derivative of the volume is directly the volume for the sphere, right? So differentiate the volume for the ball with respect to r gives you the volume of the sphere, right? Obviously in the corresponding dimension. The B1 goes to S0, B2 goes to S1, and B3 goes to S2. And that is actually not a coincidence. So there is a very intuitive reason. If you want to find the volume for the ball, then you can do something called a shell method. You can go all the way from the interior and integrate the sphere all the way to the boundary, right? So that part of integration tells you that if you differentiate the ball, the volume of the ball, then you should get the volume for the sphere, right? Okay, so now let us try to derive a general formula. We have now every technique that we needed. So let us try to find the volume for a general ball in n-dimensional space. We now know for n equals to 1 and 2 and 3, right? And also the general formula for the volume in the n-dimensional space. And it is of n minus 1 dimension. So first of all, we can in fact get a better result. We can in fact get the recursion formula. Let us see what we have done. So now let us consider the volume for the ball in n-dimensional space of radius 1. So by definition, that is basically you integrate over the solid. This is a bit messy here. We integrate over the solid B1n, which is the ball, where there's an integral here. And we integrate over 1, right? If you integrate over 1, you get the volume. And dx all the way to dx. There's n-dimensional integration. And don't be scared by this. Basically, everything looks the same as double integration. You can use the Fubini theorem to change order and do every technique you like. So in this case, I choose x1 and x2 to perform the polar coordinate. Let me change x1 and x2 to r theta. So now we have an extra r cube, right? Don't forget that. That is a differential term. And that you have 0 to 2 pi respect to the theta angle, and 0 to 1 respect to the radius. And now the interior equation, dx3 to dxn, have a boundary region. Because we restrict x1 squared all the way to xn squared to be less or equal to 1, right? This is the restriction for this domain. Because the ball is basically defined by the distance between the origin is less than 1. So now the first two guy is given to be r squared, right? So restriction for the rest of the coordinates is x3 squared, adding up to xn squared should be less or equal to 1 minus r squared. So this is a trick. This guy is actually representing x1 squared plus x2 squared, okay? So what are we doing here? We see that this thing is actually a n minus 2 dimensional ball, right? The volume for n minus 2 dimension, because you're dealing with coordinate starting from x2. So that is an n minus 2 dimensional ball with radius square root of this guy, right? So we're actually integrating a double integral over this guy, which is a volume of a n minus 2 dimensional ball with radius square root of 1 minus r squared. And we know that the volume for such ball will be the volume for the radius 1 ball multiplied by the radius to the power of a dimension, right? So what I'm trying to say is that, for example, we know that the 3D volume is 4 over 3 pi r cubed, right? And we know that the 3D volume of the radius 1 ball is 4 over 3 pi. And we know that, therefore, the 3D volume for the ball of radius r is given by the radius 1 volume times r cubed. Basically the scaling, right? Scaling in r gives you rn, where n is the dimension of the space. So in this case, the dimension is n minus 2, right? So we scale this guy by n minus 2, which is 1 minus r squared, n minus 2 over 2. The over 2 comes from the square root. And don't forget you have a r cube. R. And this is a relatively simple integral, so try to do that yourself. You can do that by substitution, maybe u to be 1 minus r squared, and then you finally get 2 pi over n in the coefficients. where you have an extra volume term here, volume of B1 n minus 2. So this is what I mentioned about the recursion formula. Actually, the n-dimensional volume, sorry, the n-dimensional ball of radius 1 has volume being the 2 pi over n times the volume of the n minus 2 dimensional ball with radius 1. So we can actually do this by iteration and to find out the actual formula for this volume. Whenever n is even, we see that the volume for the ball of radius r in dimension 2n is actually given by what I just mentioned. The volume of the radius 1 version of ball times r to 2n, right? And by our previous iteration, we know that this can be simplified to be 2 pi divided by dimension 2n, and you subtract dimension by 2. And we can do that further again. This guy will be 2 pi divided by dimension, and you have the volume of the ball with dimension subtract by 2. So we see that the coefficient is pi over n here, pi over n minus 1 here, and that all the way corresponds to pi over 2. And the rest of the thing is the volume for B12, the two-dimensional ball with radius 1, basically a disk of radius 1. So that volume is pi, right? And we can conclude from this formula, you have pi to the n. And the denominator is simply n factorial, r to n. So this thing actually corresponds to our formula very nicely. When n is 2, we see that it is actually pi. Sorry. When n is, I should write n is 1 because we're dealing with 2n. So when n is 1, this guy is pi 1 r squared divided by 1 factorial. And that is pi r squared, right? Our two-dimensional disk. Now, for an odd version, we have, again, by iteration, you have this a lot of product, and it goes all the way back to the one-dimensional ball with radius 1. And that is basically a line with length 2r or 2. So 2 here. And the r to m plus 1 corresponds to the radius r. So to simplify this guy, we interlaced some of the numbers to make the formula simpler. In the numerator, we have 2 pi to the power of n, right? And we have this 1 over 2n plus 1, 1 over 2n minus 1, all the way to 1 over 2. And those doesn't seem to be nice, so I add some extra terms to make the formula simpler. The 2n over 2n, 2n minus 2 over 2n minus 2, all the way to 2 over 2. What does that do? The denominator now becomes 2n plus 1 factorial, right? And in the numerator, if I factor out 2, you get n times n minus 1 all the way to 1, with 2 to the n, right? So you have 2 to the n here, and 2 to the n here, which gives you 2 to the 2n. The extra 2 comes from the volume for the one-dimensional ball. You have pi to the n, and then finally, n factorial, which you just investigated previously. So this will be the formula for the odd dimensional ball. In general, if I want to write everything down precisely, you have the volume of the n-dimensional ball with radius r given by pi to the n over 2 times n over 2 factorial. And together, obviously, with the r to the when n is even. And then when n is odd, we can simplify the formula above here to be this guy. So again, for example, if we deal with n to be 3, then we use the below formula here, right? We get 2 to the 3, pi to the 3, 2 to the 3, pi to the 3 minus 1, 2, 3 minus 1, 2 factorial, and 3 factorial, r to the 3. So you can see that that corresponds to 8 times pi times 1 over 6 r cubed. And that is what we desire, right? 4 over 3 pi r cubed. So these are the formulas for the ball of radius r. And in particular, to evaluate the surface area for the n-dimensional ball, which is a n minus 1 dimension surface area, then you differentiate the volume for the ball, and you get, oops, sorry. And you get that it is simply a polynomial. So you have an extra n here, and you decrease the vector by exponent by 1. The same thing happens here. The n gives uh, the n cancels out the factorial by n minus n factorial. Okay, I know this is a relatively complicated example, but it actually demonstrates a very nice fact is that after you learn two-dimensional, three-dimensional integration, you can almost do every kind of dimensional integration. It's all of the same kind of taste. You apply Fubini's theorem, you have a nice change of variable, and in this case, you can actually derive the precise formula for an n-dimensional pool. Okay, let us go back to see what we have done. So in this section, we're introducing triple integral, which behaves a lot like the double integral. And the constant boundary case is very naive. I believe you guys can do that very effortlessly because you simply use Fubini theorem to evaluate it by iterative integral. And as I mentioned, the most important thing about this section is to describe the solid. And the description based on this outside in algorithm, you first fix the exterior boundary. It can be x or y or z. And then for the rest of the two variables, you try to plot the surfaces that enclose the boundary as curves onto the diagram. So for example, in this case, I fix z, so the surfaces becomes a curve with respect to x and y. If you plot it on xy domain, then obviously the curve will depend on z, but you can describe that region using either type 1 or type 2 description. And combining that with the constant boundary, you can get yourself a description for the solid. And I believe there's multiple exercise about this in this kind of cases. So try to, if you have time, to represent this type of triple integral in other possible 5 iterations. So it can be xyz, zy, yxz, yzx, zxy, and zyx. And again, the way to do that is exactly the same. You first describe the exterior boundary, and then you try to draw every surfaces in the rest of the two variables. And then you can describe the rest of the two variable in type 1 or type 2 region to get back to the definition for E. Okay. Right. So that will be our first section on triple integral. And the rest of the theory is to work on the change of variable on triple integrals. We will change it into the spherical coordinate, the cylindrical coordinates, and then we will introduce the final formula for a general change of formula, a change of variable in every type of integral. It can be double, it can be triple, it can be a single variable. So I will see you guys in the next video.